Hello, Tensor friends. Got another problem of the day here. I want to say that all of the stuff we're doing is in some video somewhere on my channel. So you've seen this stuff before. The point is, here we're putting it all together in one place. We have one subject per video, and we do it in very great detail. So that's the difference between this and what we've done before. Is if you were looking for something on my channel, I admit it is a mess and it's hard to find stuff. I need to get it organized or get somebody to organize it for me. Anyway, the problem of the day, 621. So far we've been doing our tensor algebra, tensor calculus, and affine the coordinates. Affine coordinates are coordinate systems that are parallel. The coordinate lines are parallel. And you can see the true power of this math when you move to curvilinear coordinates. Okay? And the easiest curvilinear the coordinate to use is polar the coordinate. So that's where we're going to start because it's only in 2 dimensions. So what we're going to do, we've done before, but like I said, it's somewhere on my channel. We have a vector in the Cartesian, the coordinate, the frame. Ex, Ey basis vectors has a Vx and a Vy components. And we want to transform that into polar coordinates where we have ER, E theta basis vectors. We have a V theta component and a VR component. Okay, so these are curvilinear coordinates. All right, so we have a vector in just what we said. Here's what we want. Okay, so we want to start with the components. All right, so derive the polar vector components as x being a function of r and theta, y being a function of r and theta, and the inverse, r being a function of x and y, and theta being a function of x and y from the following diagrams. So you should come up with 4 equations from this one diagram, which is a circle with a radius, a projection onto the x-axis, a projection onto the y-axis, and an angle between the radius and this x-axis. Okay? So that's part A. Did I call it part A? Yes, I did, part A. Okay. Part B. Given the generalized equation of tensor transforms, which you've seen before, okay? So the coordinate frame is what you want. This is what you want. You want ER and E theta. And the I prime frame is what you have. So I prime is EX, EY. So if you follow this equation, you can find the ER and E theta basis vectors. I just said that. Okay, from the transforms found in part A. Now, here's something. Part C, using the Pythagorean equation of the metric, ds squared equals dx squared plus dy squared, derive an expression for ds squared in polar coordinates. Okay? So here's a hint. Use the multivariable chain rule to calculate dx and dy, as in, if x is a function of a and b, then dx would be the partial of a with respect to a, dA, right? Plus the partial of x with respect to b, dB. So if you use this multivariable chain rule with what you found from above, you will be able to calculate this in polar coordinates. All right, there's only one more. Okay, so you found the ER and E theta basis of vectors. Now you want to derive the tensor from that and compare its components to the metric found in part C. So you're going to find 4 components of the metric, the tensor, in polar coordinates, and then compare it to what you find here. Okay? All right, I'll see you in a couple days.